Okay, this is 6.6 homework, but it's from the book. Um, the first problem just wants us to graph these points in the complex plane. So the first one goes over 1 up 2 to here. Next one goes over 3 down 1 right here. So this is 1 plus 2i, and this is 3 minus I. And then the next one is negative 2, so it goes back 2 and up 2. So here's negative 2 plus 2i. And then the last one is I, which just goes over 1 and is right here. I'm sorry, actually, that just goes up 1. So that would be right here. So if your complex number is a plus bi, then you can look at this as the a-axis and this is the b-axis pretty much. So this is the real axis and this is the imaginary axis. So that's helpful because then if we want to find trig form of a complex number like number 3, we can just put it in this form really easily. Now trig forms are cosine of theta plus I sine of theta. So r in this case is going to be 3, and we're talking about pi over 2 plus I sine of pi over 2. So that point is, up 3 over none. So it's this point up here, which is exactly what you get because when you do cosine of pi over 2, that's 0. And when you do I sine of pi over 2, that's 1. So it's really 3 times 0 plus I, which ends up just giving you 3i if you go back to regular form. So with trigonometric form, it's kind of like polar, where r is the distance you go out, and theta is the angle that you rotate by. And if you put that into this form right here, you get the same thing as what you started with, but it's in a different form called trigonometric form. So our answer right here for 3. All right, 4 wasn't one of the problems. Let's move on to 6. 6, I'm going to graph this point first. It always helps me to graph them first. This goes over square root of 3, and then you go up 1. So this would be 1, this would be square root of 3 if I graph this triangle. And the hypotenuse would then be 2 because this is a special right triangle. You might notice this is like s square root of 3, and this is 2s, where s is 1. So I've got my special right triangle. I know that this is a 30-degree angle, which is pi over 6. This is a 60-degree angle, pi over 3. But I'm going to use just r and the theta because I'm going to do r cosine of theta plus I sine of theta. So the r is 2, and the cosine of the angle would be pi over 6 for the angle. Now, if you evaluate this, if you ever want to check to make sure you're right, just evaluate this. Just evaluate the cosine of pi over 6, and it's going to be square root of 3 over 2. And then if you evaluate the sine of pi over 6, we know that's 1/2. And so if you now distribute the 2, you get back to this, which was what we started with. So, you can always check to make sure that you're right, but this is our answer right here for trig form. Next one should be pretty easy because they already give us our r and our angle. So cosine of theta plus I sine of theta every time. I'll leave this one in degrees, so I'll do 3 for r, and this will be cosine of 30 plus I sine of 30. Okay, we've already kind of did this, but going the other way around, the cosine of 30 is square root of 3 over 2, so this would be 3 times the square root of 3 over 2 minus I times the sine of 30, which the sine of 30 is 1/2. So when you distribute and simplify, you just get 3 square root of 3 over 2 minus, or plus a minus, 3/2 I. So there's my a plus bi form, where a is going to be this number and b is going to be this number. Okay, the next problem wants us to do the same thing. I'm going to graph this first, so I always graph it and say, okay, where is this so I can see it. 7 pi over 6 is 1/6 more than 180. So this angle right here would be pi over 6. I know that's on the unit circle. That's negative square root of 3 over 2, comma negative 1/2. And then the hypotenuse is square root of 2 right here. So I can evaluate this then. It's square root of 2 times the cosine of this angle is negative square root of 3 over 2 plus I, and then sine of this would be negative 1/2. So now I can distribute, and this gives me negative square root of 6 over 2. If I just multiply, you can actually expand the square root over both. And then minus, I'll do minus here, square root of 2 over 2i. So that would be my answer in a plus bi form. Okay, for the next problem, I want us to find the product of these two complex numbers. And since they're in trig form, it's really easy to find the product of two complex numbers by using the formulas on our formula sheet. So pull up the formula sheet, scroll down to chapter 6, and you're going to see some formulas here. You're going to see these. This is, first of all, trig form, which we've been using. This is Duhamov's theorem here, which says if you raise some complex number to a power, this is what you can do to make it easier. And then this is the nth root of a complex number. Now, what I don't have on there is the product and quotient of complex numbers, which is right here. I don't have it on there because I think it's pretty easy. All you do is multiply the r's together and then add the thetas together. And that's it. When you divide, you do the same thing. You divide the r's and subtract the thetas. So I don't have this on there, but hopefully it's easy enough where we can memorize it. So the answer to this one, then would be we'd multiply the 7 times 2 and get 14. And then we'd add the angles. So 25 plus 130 gives 155. And we can leave it right in trig form. Then the next one, same thing. 5 times 3 gives you 15. And I'm going to have cosine of the two angles added together, which I don't know what that is yet, so let's find that. Pi over 4 plus 5 pi over 3. Need a common denominator, so let's multiply the top and bottom of this one by 3, so it'd be 3 pi over 12, plus multiply top and bottom of this one by 4, it'd be 20 pi over 12, so 23 pi over 12. And then we can just write that down, I sine of 23 pi over 12. And that's it. And when you're dividing, you just do the quotient of the r number, and then you subtract the angle. So it's theta 1 minus theta 2, which is the numerator over denominator, so it's going to be negative 30 in this case, which is cosine of negative 30, plus I sine of negative 30. Next one then would be 5 halves, the cosine of 105, 220 minus 115, plus I sine of 105. Okay, the next one wants to do 27 two different ways. So regular multiplication for part B using standard forms. I'll do that first, actually. When I FOIL these out, I get 3 minus 2i times 1 plus I, and I have to FOIL, so 3 plus 3i minus 2i plus negative 2i squared. This turns into 3 plus I, and then this simplifies to negative 1, so it'll be plus 2, which simplifies to 5 plus I. So for part A, I need to convert both of these to trigonometric form. So 3 minus 2i goes out 3 and down 2. So we're talking about this right here, where this is 3 and this is 2. The Pythagorean theorem would give us the square root of 13 for the hypotenuse, and inverse tangent for the angle, which ends up being negative 0.98 about. So I know I'm going to have to round this, unfortunately, so it's not going to be that pretty. But so in trig form, this would be r cosine of theta plus I sine of theta, so it'd be square root of 13 times cosine of negative 0.98 plus I sine of 0.98. And then I want to do the other one as well, so I'm going to regraph that one. That one goes over 1, up 1, which is right here. And then obviously this is your special right triangle, 45, 45, 90. So if this is 1 and this is 1, this is the square root of 2. S and S square root of 2. And then the angle is 45 degrees, which is pi over 4. So that complex number is cosine of pi over 4 plus I sine of pi over 4. Now, when I multiply complex numbers, I multiply these together, so it's going to be the square root of 26 times the cosine of the two angles added together. So I need pi over 4 plus negative 0.98, which gives you negative 0.197 about. I know this isn't the prettiest, but that's what I'm going to have to use here. Negative 0.197. And then let's just double check that this works. So let's FOIL this through, do the cosine of negative 0.197 in your calculator, and multiply by the square root of 26 to see if we get this same thing here or close to it. And we do. You get 5 plus I if you evaluate this and multiply. And it'd be perfectly 5 if we didn't round this. But I actually didn't round. I kept it in my calculator and it worked perfectly. Gave me 5 plus I. So it turns out these are the same ways. It turns out this way was actually easier for this one because of all the weird decimals here. And the conversion that needed to take place, but both ways will get you the same answer. It turns out that this is the trig form of the multiplication of these two complex numbers, and this is the regular a plus bi form. Okay, so we can do this again, this time with the quotient. So we can do the first one, 3 minus 2i over 1 plus I. Now I'm going to multiply both the top and the bottom by 1 minus I, because that doesn't change the number at all, and that helps me simplify. So if I do that, I'm going to FOIL the top, in which case I get 3 minus 3I minus 2I plus I, plus 2I squared rather, right here. The last one, last times last. And then I can simplify that, but first let me do the bottom. When you FOIL the bottom, you get 1 minus I squared, because the middle terms cancel. If you simplify this, this is -1. These add together, so you end up getting 2 minus 5I in the top. All over, this is -1, so you end up getting 2 in the bottom. So this simplifies to 1 minus 5 over 2I in standard form. Now let's make sure we can get that with trig form by dividing these two complex numbers. When we divide that, we get square root of 13 over square root of 2, which I can rewrite as square root of 13 over 2, and then cosine of, now the angle I have to subtract, -0.98 minus pi over 4, -1.77 about, plus I sine of -1.77. And now I can double check that this is the trig form and that this is the regular a plus bi form. Double check they're the same by multiplying through. And they are, had it not be that I knew how to add, because this is -2, so this should have been 1 right here. And then I get the same, because I get 0.5 up here plus -2.5i, which is the same thing as this. So I just had one mistake right there. Okay, next is Duhamov's theorem for the indicated power. So we're going to raise this complex number to the third power. That formula is right off your formula sheet right here. It's really easy when it's in trig form, because the r, which r is 1 here, it's not written, so there's 1 in front. So it's just r to the nth power, so n is up here, so it's 1 to the third power, times the cosine of our angle theta, but times n times the power, which is 3, so it'd be 3 times theta, which is 3 pi over 4, plus I sine of 3 pi over 4. So you don't have to write the 1 to the third, I could get rid of that, but there's your answer. It's pretty straightforward. I can do, it's a little harder when it's like this, because I have to turn it into trig form first. So I have to take the 3 plus 4i and find the r and theta. So my r is the 5, and then my theta is about 0.93 radians, or 53.1 degrees, whatever you prefer. So in trig form, this would be 5 cosine of 0.93 plus I sine of 0.93. And I want to raise that to the 20th power. So now I can just use this formula up here. It's 5 to the 20th power times cosine of, it's going to be 20 times 0.93, which gives me 18.55. So it's pretty easy to use this formula to raise it to the power, rather than obviously multiplying all these out yourself by foiling. It would take forever. So there's our answer in trig form. Okay, the last thing is finding the nth root of a complex number, which is, once again, just plug into this formula. The only tricky thing is, if you're taking the fifth root, there's going to be 5 of them. So if you want to find the first one, that's where you're going to use k equals 0, and you'll use k equals 1 for the second one. You'll follow that through. So for the first one, I want the fifth root of 32 right into this formula, times the cosine of theta, which is pi over 2 in this case, plus 2 pi k, but k is 0, so that's going to drop out for the first one, divided by n, and n in this case is 5. So I could simplify this to 10, and then write sine of pi over 10. So you have to keep doing this now. I know it takes a little while, but the next one would be the fifth root of 32 times the cosine of our angle, which is pi over 2, that's our theta, plus 2 pi times k, where k is 1 now, all over our n, which is 5. So I have to simplify this right here. And when I do that, I get just pi over 2 here. So now I repeat it when k is 2. So the third complex root would be the fifth root of 32 times the cosine of our angle pi over 2, plus 2 pi times 2 in this case, all over 10, or I'm sorry, all over 5. And then I can simplify this once again by adding this together, which gives you this. And then the next one, fourth one. And the last two would be this right here if you simplify them. I run out of time in the video, so I hope this helps.